weeks ago. Thank you, scary voice. So I reached out to Daniel a few weeks ago and said, hey, you did this really cool T-Rex work. Do you think we could chat? And he replied by reminding me, actually, we've met before, at least twice. Oh, man. So I've been following Daniel's work, even though I forgot his face, for a few years now. He's doing some really cool stuff in inverse reinforcement learning and thinking about humans. And he also is a former collaborator with Prabhat, a new student here. He only has one paper with Peter Stone, but I won't hold that against him because he went to UT Austin and did lots of cool stuff with Scott Niekum. And now he's a postdoc at Berkeley with Anca and the other person I didn't know, Anca, Dragan, and Ken Goldberg. So with that, I think I'll stop talking and hand it over to Daniel so he can tell us about some of the cool stuff he's been doing.
Awesome. Thank you, Matt, for that kind of introduction. So yeah, let me share my screen. And okay, can everybody see that?
Yep, that looks great.
Cool. All right, yeah, so I'm Daniel. Today I'm going to be talking about some of the work that me and my collaborators have been doing on this idea of efficient and robust learning of human intent. And so one of the things that motivates a lot of this work is that we as people live in a fascinatingly complex world filled with all sorts of different tasks and things that we like to do. And everybody has kind of their own ways of doing things. Everyone has different preferences, different goals. And ideally, we'd like to get our friendly Mr. Robot here, or in general, any autonomous system out into the world, interacting with people as they perform a variety of tasks and learning from them, learning about their preferences. And this is often really challenging because often the robot doesn't really know what the human wants initially. And often the human can't really write that down. If you think about trying to write down a cost function for how to drive, how to make your favorite salad, or something like cleaning and organizing your house, or even just lifting a patient onto a bed. These are complex tasks that we as humans can do pretty naturally, and it's easy for us to kind of show people and explain them, but really difficult to write down a mathematical function or something that defines performing these tasks really well. And so this motivates this idea of imitation learning from human data in order to teach agents a policy, which I'll denote by pi, as a means of acting in the world. And you can kind of roughly break imitation learning into two different settings. One, I'm going to call behavioral cloning. And this is the idea that I want to map from observations of states and actions to a policy just using standard supervised learning. So I want to train a classifier or regressor that will take an action and predict the action I should take, a state, and predict the action that I should take. And this is often pretty efficient, but can suffer from compounding errors and doesn't really actually learn kind of the intent behind the human data. On the other hand, there's this idea of inverse reinforcement learning, where you can see we now have this R here in the middle. And so the idea being that we want to take this data, maybe demonstrations, and we want to infer the reward function or cost function that is motivating the human in providing these demonstrations. Given that reward function that models the human's intent, we can then run policy optimization, say maybe using reinforcement learning to get a policy. And I'd argue that if we're interested in safety and robustness, that this is a really nice setting because now we're actually able to reason about costs and rewards, reason about intent. And in particular, if we're thinking about this setting of learning a reward function to get a policy, I'd also argue that we probably should just learn one reward function. Humans are often ambiguous. We probably want to be Bayesian, if possible, about this. We want to maintain uncertainty, have a belief distribution over likely intent, likely reward functions, given this human data. And so this kind of motivates a couple different research challenges, which I'm going to touch on today. And so the first one is, how do we represent this uncertainty? Then given this uncertainty, what can we do with it? Well, one thing is we can try and be robust to this uncertainty. And I'm just going to denote that by these big buff arms, but I'll talk about a little bit later about what it might mean to be robust. And then the second thing we might be able to do is say, okay, I have this uncertainty. I also have this human here, so let's ask for some help and let's actively try and reduce this uncertainty by doing active queries. So we're going to start off just talking about how can we represent this uncertainty. And so we're going to be Bayesian about this. So we want to have a posterior distribution over likely reward functions given this human data D. And so we can use the Bayes rule, which we all know and love, where we can say that this is going to be proportional to a likelihood function. What's the likelihood of seeing that human data given that the human is trying to optimize a particular reward function R, and then a prior, which gives us some information about just how likely in general do we think different reward functions are. And like I said, we want to sample, or at least have a distribution over reward functions that look likely given this data. And so you can go back to 2007, and there's a nice algorithm called Bayesian inverse reinforcement learning that does exactly that. And they make a couple of assumptions here. The first one is they're going to assume that the demonstrator is Boltzmann rational. Basically what that means is they're noisily rational, but they're more often than not going to take the right action. And so this kind of boils down to modeling the demonstrator via the softmax policy with an inverse to temperature parameter beta. And so kind of dig into this, we have, in terms of notation, Q star is going to be just the standard Q star from reinforcement learning, which is how much reward under this reward function R will I expect to see if I take this action A in state S and then act optimally thereafter. And you can see here we have this fraction. So in the numerator, this is essentially a representation of how good is what the demonstrator did under this reward function R. So I'm taking this product over all state action pairs in these demonstrations. And then in the numerator, it's like how good is what the demonstrator did. In the denominator now, I'm comparing that to all the alternatives. So if I look at all these actions B in my action set A, how good are those? And so quite naturally, this gives a higher likelihood to reward functions that make the demonstrations look more optimal. If I have a reward function hypothesis that makes what the demonstrator did look a lot worse than alternatives, I'm going to downweight that. It's going to have a low likelihood. And so you can use this likelihood function to run Bayesian inference to generate lots of likely reward functions given data. But a question here is how tractable is this in practice? And so if we look a little deeper into this likelihood function here, this is the likelihood of the human producing demonstrations when trying to optimize R. And if you've taken a reinforcement learning class, this probably kind of sounds familiar, or like an optimal control class. This is basically solving what's often called this forward problem, which is, given a reward function, can you find a policy? And so this is often going to require reinforcement learning, which is already a really hard problem, in the inner loop of this even harder problem now of finding a reward function. So can we do better? So back in 2019, we had this idea of trying to kind of switch around the problem a little bit to make it a lot more efficient. And so rather than just looking at demonstrations, we said, well, what if we have a little bit extra supervision in terms of ranked preferences over demonstrations? And this has a couple benefits here. One is that this allows us to actually extrapolate. So in a normal inverse reinforcement learning setting, like we talked about, we're going to try and find a reward function that makes the demonstrations look optimal. But what if the human isn't optimal? What if they aren't that good at the task? Well, if I have some rankings over really awful to mediocre demonstrations, I could potentially pick up on what makes these good and bad and actually extrapolate and say, well, I think I could actually maybe think about what might be even better than what you've shown me. Another benefit is that this is going to make things a lot more efficient because it's going to remove this requirement of having reinforcement learning there in the inner loop. So we call our algorithm trajectory ranked reward extrapolation, or TREX, where the idea is that we have this set of ranked demonstrations. So here's an example from the half cheetah domain, where we want to get this little robot, the simulated half cheetah, to run as fast as it can to the right. And so I give it a set of pre-ranked demonstrations, starting from just awful, it's kind of scooting on its head, not doing very well, up to mediocre. So this is the best demonstration we showed it. It's kind of like a little kid who runs around really excitedly and occasionally face plants. And the idea is we want to learn a reward function from these preferences over a set of demonstrations. Given that reward function, we then want to optimize a policy. And so when we plug this reward function into PPO, the TREX policy that's learned actually runs about twice as fast and far as the best demonstration. So it is indeed able to extrapolate what the true reward function should be given these preferences. So how does this work? So we've got a set of ranked demonstrations. Even more generally, we could just have a set of pairwise preferences. And so if we hone in on a set of pairwise preferences where I prefer trajectory 2, tau 2 over trajectory 1, what does that actually mean? Well, if I were to look at the rewards under all the states in trajectory 2 versus all the states under trajectory 1 and accumulate those, add those up, ideally I want the accumulated return, the rewards here, to be bigger for my more preferred trajectory and lower for my less preferred trajectory. And so we can train this via backpropagation using a deep neural network for our reward function approximator, just using a standard pairwise ranking loss, where I'm trying to make the accumulated returns of the better ranked trajectories higher than the lower ranked trajectories. And one natural way of thinking about this is as a classification problem, where I'm using these accumulated returns as the logit values in this binary classification problem, where you hand me 2 trajectories and I want to predict which one you would prefer. And so what's nice about that is that we can actually train this without needing RL in the inner loop. We're basically just given some supervised data. We're training this reward function, and we want to just see how well our accumulated returns turned into logits match up with the actual preferences. And so what's nice about this is it allows us to scale to visual domains as well. So I have this autonomous driving, in quotes, example in Atari, where here we don't have access to the score. We're masking that. We give 12 ranked demonstrations, where this is the best demonstration that we show it. It's decent, but it's not great. It's not going as fast as it could. Occasionally it's gonna hit cars. It's a little uncertain. And we train on this, learn a reward function, and then plug it into reinforcement learning. And the T-Rex under the ground truth reward, which again is not revealed to the agent, does a lot better. It's able to really quickly learn that it wants to avoid cars, it wants to go fast, and gets a much better score. So this is really cool. We now have a way of learning reward functions given access to these ranked demonstrations. But one natural question is, what if I don't have access to these nicely ranked demonstrations over a wide variety of skill levels? So one thing that we also looked at is, well, maybe you can just learn by watching someone learn. So if I'm watching an RL agent, or maybe just a human who's starting off as a pure novice, and they're getting better and better at a task slowly over time. So you can see here, this is the Hopper domain. I'm showing some snapshot rollouts over time from a reinforcement learning agent. You can see, it's slowly getting better and better, but still not actually achieving the goal, which is to continuously hop as far as it can to the right. So if we're actually watching this agent over time, we can get some nice weak supervision in terms of just the timestamp. So if I assume that on average, you're improving over time, this actually gives me some weak supervision that says that, hey, something later that I see you do is probably on average better than something really early. And so this gives us preferences. We can then plug these into this T-Rex framework. And we've shown that this works really well when watching an RL agent learn. And I think it's an interesting open question of whether we can actually do this with real people by watching them start off as a novice and get better at a task over time, which is something that I'm interested in looking at in the future. Another idea that we've looked at is, well, maybe I don't have any timestamps. Maybe I don't have any supervision at all from a human. Let's just consider the general imitation learning setting where I have just a big bag of demonstrations. And so one thing we can do here is, under the assumption that the demonstrations are better, hopefully significantly better than a purely random policy, is we can look at this idea of injecting noise into a cloned policy. So we talked earlier about one of the ways of doing imitation learning is just to use supervised learning and take a data set of states and actions and learn via neural network or linear regression, whatever we want, some mapping that goes from states to actions. This gives us a policy now that's actually a program. We can mess with it, we can do whatever we want to it. And so we can actually add noise. In this case, we're adding epsilon greedy noise. So with some probability epsilon, we're having the policy take a random action. And with a probability 1 minus epsilon, we're taking the action that it thinks it should take based on the supervised training. And this is kind of cool because it provides automatic rankings as noise increases. So you can show that as you add more and more noise, an expectation the performance is going to be worse. And at some point, you're going to get to the performance of a purely random policy. So assuming that your demonstrations are better than random, you can kind of interpolate between purely random and something close to what the demonstrators gave you. And you can generate as many rankings as you want now. So we call this disturbance-based reward extrapolation, or DREX. Whereas I've talked about, we start off, we do behavioral cloning to get a policy. We then add, in this case, less and less noise. So I'm going from a high epsilon of 1, which is purely random, to a really low epsilon, which is almost always following the behavioral clone policy. And we now have these implicit rankings based on the noise level. We can then take these, plug them into T-Rex again, learn a reward function, and then optimize a policy. And we show that over a variety of tasks, this actually often does much better than the demonstrations by kind of learning via this noise injection what's good and bad, and kind of pushing the policy to stay close to the demonstrations and perhaps even extrapolate a little bit farther. But there are some problems here. And so you do see some interesting reward hacking. So this is an example from this Atari game called Beam Rider, where the agent learns that it can mash these keys and go left and right really fast, and it stays out of the firing lanes of the oncoming aliens. And it's able to like live forever, but like never scores any points. And so here it's like picked up on the fact that like, hey, getting hit by the enemy aliens is really bad. Like making it to, for a long time in this game is really good. But the reason here is that probably T-Rex is just finding a maximum likelihood estimate of the reward function. This like makes the rankings, makes sense. It's like, hey, like if I just pick up on like whether I got hit or not by an alien and how long I lived, that allows me to explain the rankings, but it doesn't actually extrapolate in the right direction. One of the problems here is that there's like no consideration of, alternative hypotheses or like what kinds of different possibilities there might be behind the rankings. And so that's like going to motivate the next section of the talk, where we're going to talk about, can we combine the best of both worlds? So can we take what's good about T-Rex and D-Rex, which is computational efficiency, better than demonstrated performance, and combine that with what's good about Bayesian IRL, which is the fact that it returns this posterior distribution over possible reward functions, which enables us to think about risk and uncertainty analysis. And so before I jump into this, I think this is a natural point to pause and see if there are any questions.
We've got a question in the chat.
Perfect.
Do you want me to read it out, or do
Yeah,
you?
that would be great.
Okay, sure. How does it learn that the cheetah falling over like a little kid trying to walk in the best demonstration isn't actually part of the optimal desired reward function if there are no demonstrations when the cheetah doesn't fall?
Yeah, that's a great question. So we have, I think in this case, we gave it about 15 demonstrations, ranging from like that awful kind of like faceplant scoot up to the one that like occasionally falls. And so the idea here is it's trying to essentially classify, given two trajectories, which one is better. The only way to do that is to really kind of figure out, what makes these different. And so it's going to hopefully notice that like, hey, trajectories that fall down less often are better than trajectories that fall down more often. Trajectories that make more progress to the left are better than trajectories that make less progress. And so this way it's able to actually pick up on the fact that, hey, like maybe making fast progress to the right with like fewer falls is better. And so having that reward function is what allows it to extrapolate and say, well, maybe I can, by running RL and exploring, if it's able to find a policy that like never falls down and runs really far to the right, it's going to assign that a really high reward, and it's going to converge to a policy that does that.
Got it. Thank you.
Cool. Yeah, that's a great question. So we're going to jump now into this idea of a Bayesian version of T-Rex. And so idea here is we want to do fast Bayesian inference, and we're going to leverage the niceties of preferences, also with learning a low dimensional latent space, which will allow us to do really fast Bayesian inference. And so we call this Bayesian reward extrapolation, or Bayesian Rex. And basically the idea here is that we're still going to be dealing with high dimensional, in this case, image inputs. We're going to have a set of ranked demonstrations that we get from the user. And we're going to learn this feature embedding, this latent space, where we have this trainable convolutional neural network. And we're going to train this feature embedding using a variety of different unsupervised and self-supervised task losses. And so in this case, we tried a variety of things, and we found that kind of having this nice blend worked the best, where we have this autoencoder. We use a temporal distance metric, which is just taking two states in a trajectory and trying to predict how far apart they are. And we also learn an inverse dynamics and a forward dynamics model. And we also learn based off the T-Rex ranking losses. And so all of these losses are going to share the same feature embedding, but have separate heads to predict their respective losses. And the idea here is if I can learn a feature embedding that is useful in solving this variety of different tasks, then hopefully this is capturing a lot of the interesting features that are part of this domain. And hopefully like the different features that might explain, shooting aliens versus getting hit by aliens, or like, living a long time and different things like that will all be hopefully encoded in this feature embedding. And so what's nice now is we can train this offline using this, self-supervised task classes. We can then freeze the weights. And now we just have this feature embedding that takes a high dimensional input, embeds it into a lower dimensional space. And this gives us a reward function that could be linear in these, highly nonlinear features. So we can just have a single linear layer on top of this to get our reward function. And so what's nice about this, by having a linear reward function, we can then just take all of our pre-ranked demonstrations and we can embed these demonstrations in this latent feature space by simply accumulating the expected feature counts over time for these different trajectories. And this can be done as like a pre-processing step. And so we now have these like expected feature counts over this embedding space for every demonstration I've seen. And so this is going to make our Bayesian inference a lot more efficient. So a standard Bayesian inference algorithm like Markov chain Monte Carlo, or MCMC, is essentially going to be taking these steps in this weight space. Is going to be like proposing different reward functions, and it's going to be saying, how likely is this new guess of what I think the reward function might be. And if we can make this fast, then we can make this Bayesian inference really fast. And so what's cool is if we have all of these demonstrations that we've kind of pre-computed their expected feature counts, you can show that if you have a linear reward function, the return of a trajectory is simply going to be that the weight vector multiplied by the expected feature counts of those different trajectories. And so this gives us a ranking loss now, where we're saying, okay, what's the probability of preferences, which I'm denoting by the script P, over demonstrations, given a weight vector. And this weight vector is that linear layer on top of this feature embedding. And so we can then propose different weight vectors. We can evaluate their likelihood, and we perform this Bayesian inference to sample a lot of likely reward functions given the preferences in the demonstrations. And so this is really cool. I can run this on like my laptop, generate 100,000 samples in just 5 minutes. Whereas if I were to actually take like the standard Bayesian IRL approach, where I'm actually running deep RL, that would take 5+ hours to generate each sample, which is just intractable. And so this is cool. We can actually now run Bayesian inference really fast. And we can now use this to think about stuff like, well, what if I want to come up with high confidence, maybe performance bounds for a variety of evaluation policies? I can use this distribution over reward functions in order to say, okay, what's the distribution over expected return for a variety of different policies or different trajectories? As one example, I generated a couple of demonstrations myself of something that's like trying to be good. I'm not that great at this game, but I tried to shoot the aliens, tried to avoid getting hit. Something that's like mediocre, where I don't get like the best score, but I'm doing an okay job of avoiding getting hit, trying to shoot some aliens. I also tried giving like a really deceptive demonstration, where here I'm like trying to shoot and move around, but actually not hit any of the aliens. But I'm also trying to not get hit by the aliens. And then a pessimal one that just gets hit as quick as possible. And so given these 4 different trajectories, the idea is, can having this distribution help us in terms of ranking these, in terms of which ones we would prefer over others? And if we're able to, by performing these high confidence bounds, given these distributions from Bayesian Rex, we are able to accurately rank these from best to worst. And in particular, it's nice that like this deceptive demonstration actually is ranked lower than like the mediocre or like the good one. And so having this distribution over possible reward functions allows us to identify that like this deceptive one, and while it might look good under a couple reward functions, doesn't look good under a lot of others. And indeed, we found that you can also use this as a way to detect potential reward hacking or gaming behaviors, where if you look at the distribution over expected returns for like a policy that looks like this, you'll see that has really long tails. And so while it looks good under some reward functions, it looks really bad under other reward functions, like the reward function that says that the only thing that matters is shooting the enemy ships. And so this gives us a way to like identify that, hey, maybe something fishy might be happening here. And so given this uncertainty, there's still a question of like, how should the agent act? So I've talked about how we can use this distribution of reward functions to maybe like rank different policies, to maybe identify when a policy might be like not satisfying a lot of the reward functions in this hypothesis space. But there's also still kind of the question of like, what if I want to like directly optimize a policy? And so this brings us to like the second point here, where we want to be robust under this uncertainty. Ideally, we want to perform robust optimization. And so we've shown that we can get this distribution of likely reward functions. And so the question is, if I have a bunch of reward functions that I want to try and optimize with respect to, how should I do that? What does it actually mean to be robust? And so our approach here was to take some ideas from finance, which has lots of interesting risk metrics, because they're very interested in risk here. And so if I think of X as the policy performance, there's this notion of value at risk, which you can think of as just like a quantile. So given, in this case, alpha is going to tell me essentially the area under my probability distribution that's to the right of the value at risk. And so the higher the alpha, the more into the left tail I'm looking. And so since this is performance, I don't want to be in the left. And so the value at risk is going to tell me essentially like what's the 1 minus alpha quantile in terms of my performance. And this is like a pretty natural way to think about risk. I might say, hey, like 95% of the time, I'm doing no worse than like X amount. But optimizing for value at risk ends up being pretty hard. So what we do instead is we take this idea of conditional value at risk, where conditional value at risk is saying, okay, conditioned that I'm in this tail, like in this like 5% worst case outcomes, on average, how bad are things performing? So this is nice because it's not just kind of ignoring the ends of the tail. And it turns out that you can actually use CVAR to come up with a convex optimization problem, which is going to make our life a lot easier. And so the question here is, how do we solve for robust policy? So we proposed an approach that we called Bayesian robust optimization for imitation learning, where we propose to blend between these two different objectives, where one is on the left here in blue is just expected performance. So I want a policy that does reasonably well in expectation over these different reward functions I think that are likely. But then we also have this robustness term on the right in orange, which is the conditional value at risk, which says if things get really bad, how bad might they be? And so in terms of reward functions, it's saying, are there some reward functions under which I'm like, my policy, pi theta, is actually performing really badly under? And you can see that we can kind of blend between these two via this lambda term. So if really we just care about expected performance, we can make lambda 1. And then we're essentially just doing a standard Bayesian inverse reinforcement learning algorithm where we just optimize for the expected reward under the posterior. If lambda is 0, then we're going to say, hey, I'm really just interested in robustness. I don't want to do really poorly under any of these like reward function hypotheses. And we can like also put lambda in between to get some blend. And what's cool about this is you can actually formulate this as a nice linear programming using like the dual form of MDPs, and you can just solve this really efficiently as long as you have a discrete MDP and you know the transition dynamics. And so we were interested in trying to extend this to cases where I have continuous states, continuous actions, and I don't know my transition dynamics. And so this leads us to this idea of policy gradient Broil, or PG Broil. And so if you're familiar with policy gradients, we have this standard kind of form of just the vanilla policy gradient where we have this advantage function here, which is telling us kind of how good are taking actions A in state S. And I want to like improve my policy. So I want to increase the likelihood of taking actions in states that have higher advantage than the other actions. And so what we found is you can actually formulate a very simple or very similar and also simple objective by taking the policy gradient of the Broil objective that I showed earlier, where essentially it boils down to having a tail risk weighted advantage. I don't want to go into all the details, but essentially what this means is I'm going to be updating my policy and putting more weight on these reward functions under which I'm performing the worst under. And this easily extends to like a PPO style policy gradient update. And it's just pretty easy to kind of plug into standard policy gradient algorithms that are out there, allowing you to optimize with respect to a distribution over reward functions. And so as kind of a nice kind of example that's visual, we looked at this problem where we have a known goal that we're trying to get to. We're trying to minimize our distance to the goal, but we have this gray region, which has uncertain cost. Most of the time, like 90% of the time, we think it's like not that costly to go through, but there's like some small 5 or 10% chance that we think the gray might be like really costly. And so if we look at what our policy does for different values of lambda, if lambda is 1, remember this just results in the expected performance over the distribution. So I'm going to say, hey, in expectation, it's not that bad. I'm just going to cut through, take the shortest path cost to the goal. As I increase lambda, all of a sudden I'm a little more wary about spending a lot of time in this gray region because there's some chance that might be painful or like have a high penalty. And so you can see that as lambda goes to 0, now I'm just paying attention to robustness. And I'm saying, okay, there's some chance that gray is really bad. So I'm actually gonna like take a little bit of a hit and take the long way around just to make sure that like my tail risk is like really low. And so this is kind of nice. We can blend between these different behaviors depending on the risk sensitivity of the user, depending on the particular task that we're in. Another thing that we found is cool is having this policy gradient approach that's trying to balance multiple objectives. It actually kind of gives you this natural hedging against different objectives. So we looked at this Atari boxing game here, where there are kind of like different objectives in terms of like trying to avoid getting punched by the opponent. You also want to like score punches yourself. And we gave just a couple suboptimal demonstrations and gave preferences over these. And we found that over a wide variety of different baseline algorithms, they really get confused given like these pairwise preferences and often just kind of attached to a single objective of either like trying to run away from the other agent or just trying to avoid hits. Whereas we found PG Broil really tries to balance both. And so it tries to avoid getting hit as well as scoring punches, allowing it to score a lot higher in this type of game. And so, yeah, so I think this is another natural stopping point if there are any questions here.
I've got a conceptual question. If I'm using inverse reinforcement learning to learn one reward function, there could be an infinite number of reward functions that fit the demonstrations I've seen. Am I remembering that correctly?
Yeah.
Okay. So then when you're talking about when you've got a distribution over reward functions, how does this work? Do you have a distribution over a set number of the most possible reward functions? Is this a distribution over every single possible reward function?
Yeah, that's a great question. So, yeah, so for the Bayesian Rex work, we have a distribution over these weight vectors. And so we're doing Bayesian sampling where we're sampling weight vectors and we're kind of like doing this Markov chain walk through the weight vector space where we're going to say, okay, let's like add some noise to our weight vector, see if that makes things look more likely or less likely. And we are enforcing a norm constraint on these weight vectors because one thing you could do is you could just kind of keep on increasing like the magnitude of the weight vector and say, hey, this looks better and better and better, because you can like scale a reward function and it's going to lead to like kind of the same optimal policy. And so like ideally we don't want to have that. And so to kind of like restrict the range of things that we're exploring, we do have, I think in this case, like an L2 norm constraint on these weight vectors. So we're exploring like the L2 like surface of the ball. And so that's one way of like trying to avoid just kind of like scaling a reward function to get like a bunch of hypotheses that all kind of result in the same idea. So I don't know if that answers your question, but I think, that's kind of the main thing that we're doing here. And then we're also, we are, using this like Gaussian proposal distribution to try and sample a wide range of reward functions. And there's no guarantee here that like some of these won't like converge to the same policy, but the hope is that, we're going to explore a wide enough space that we do uncover a wide variety of reward functions that would, potentially lead to different behaviors.
And hopefully eventually cover the behavior that's actually optimal.
Yeah, hopefully, within that space, I'm going to assign a high likelihood to like what the human's true intent is. But that might not always be true. And so I think that kind of naturally like leads in to like my next point, which is like, what if there's just like too much uncertainty? What if I have
Daniel.
like kind of a uniform distribution still over like all sorts of different, possible reward functions, or maybe like just given like biases in the data, maybe I don't assign like a high likelihood to like what the true human really wants.
Daniel, there is one question in the chat box.
Okay, yeah. Before I jump in, what's the question? Can you read it?
Sure. Is there importance on trying to capture a spread in performance in the rank demonstration? comparing expert trajectories against each other versus including novice and intermediate trajectories as well. This is from Michael.
Yeah, so we've definitely found empirically that having kind of a pedagogic set, you might say, of like ranked demonstrations, kind of showing good and bad and mediocre things and giving preferences over those definitely helps. If you just have all like expert demonstrations, there'll be like, slight differences between them. But yeah, really having like examples of good and bad behavior, I think is what really helps. And so, yeah, so I don't have anything like conclusive to say on that, but like anecdotally, yeah, we found that that can make a big difference. So yeah, great question. Okay, so yeah, so what can we do if maybe like, our robust policy is just trying to be robust to everything? That's probably gonna like kind of lead to nonsensical behavior. And so this leads to this last and final research challenges, which is how can I actively reduce this uncertainty? I wanna ask questions, I wanna collect more data in order to reduce my uncertainty and kind of hone in on what the human really wants, what the true reward function is. And so one thing you can do is you can kind of take this approach that we've talked about before, where you do Bayesian inference, you sample different policy performances, you come up with some measure of risk, and then you can find states that have like the highest risk, and you can actively query made for demonstrations starting in these different states. Or you can like roll out your own policy from these different states and ask for a critique from the human and say, what parts of that were good or bad. And this is something, that we looked at back in Coral in 2018. And this works pretty well, but this was still using kind of a classical Bayesian IRL approach. And so it did have some inefficiencies. And one of the main inefficiency here is that like optimizing policies, using RL is expensive. And even if I don't have to run RL to get every single sample, I probably have to rerun RL when I collect some more data. And so this could be problematic if these RL rollouts are expensive or possibly unsafe. So one of the ideas that we had to address this is, well, what if we just kind of go offline? Let's just do offline RL and offline reward learning. And so offline RL has been shown to work really well, where you have this data set of offline trajectories. And T-Rex, you can think of that as an offline reward learning algorithm, where I have this offline data set of preferences, and then I'm learning a reward function. And so we proposed this approach that we called Opal, or offline preference-based apprenticeship learning. But the idea is that I have an offline data set of potentially lots of different agents performing lots of different tasks, maybe optimizing lots of different reward functions. Maybe some of this is human demonstration data. And essentially, I want to use this data set, and I want to search through it to find pairs of trajectories that I can then send to a user and ask them to give me preferences over those. And so by collecting preference labels, I can then learn a reward function, just like we did with T-Rex using this preference rank loss. I can then use that learned reward function to go in and label all these transitions, which I'm assuming we don't have reward functions on them. If we did have reward functions, we're assuming that these are someone else's reward function and not this particular user's. So we're just going to assume that we have this data set of state action, next state transitions. And by repeating this process, by learning a reward function, then thinking about where I have uncertainty, looking for new trajectory snippets from my offline data set, showing that to the user, I can refine this reward function over time. And then after performing this active learning, I can run offline reinforcement learning to get a policy. And so this requires no interaction with the environment. It doesn't require me to roll out any trajectories in order to learn a reward function or to run a policy. And so what's cool about this is you can take something like the cart poll, where we just generated a couple, I think maybe 100 random trajectories. And then we wanted to teach it to do this windmilling behavior. And so giving it preferences over time, it's able to learn by kind of stitching together things that it's seen in this offline data set, along with the learned preference, how to do a decent windmill behavior here. We also looked at some of the kind of tasks in D4RL, which is a database of different tasks, and showed that we can actually learn the reward function. And it doesn't always work. As you'll see here, it kind of learns how to do part of this task. In this case, you're supposed to open the door, I think move the little teapot, and then I think you're supposed to open another door. And so we kind of get part of the way there, but this is kind of cool that we're learning this all without any of the true reward signal. But I think like the real power comes in is if I have like a data set and I'm able to like really kind of like repurpose this for something else. And so as a simple example of this, so in this like D4RL, which is like a database of offline RL problems, they have this idea where it's this kind of point mass environment where you're trying to move like this little point mass robot in continuous space and get it to like a particular goal. And the way they generated the offline data was essentially they have this kind of like 4x3 grid of different points, and they're just kind of randomly selecting points that they move it to using just like a hard-coded controller. And so the data kind of looks like this, where the agent is, moving from one point to another point and going around. And so the question is, can we use this to teach the agent to do something new? And particularly, we wanted to teach it to do these counterclockwise orbits around the area. And so we do active pairwise preference queries where we'll show the human a pair of trajectories and say, which one do you prefer? In this case, blue is preferred over red because it's kind of doing part of this like clockwise or counterclockwise orbiting. Similarly, we might show a preference like this, and the human might say, okay, yeah, I want to like kind of stay along the edges, so I prefer like the blue rather than the red. And we do this over time. And then what's cool is we can actually learn a reward function. And so we're visualizing here the reward function that we've learned. And so then we pass this into offline RL, which takes the data that's seen in this data set, has this reward function. Now it can try and stitch together these different pieces of trajectories in order to get a behavior that is a pretty good approximation of what the human wanted in terms of doing these orbiting behaviors, which is pretty cool. So kind of going back to this problem though, that like RL is time intensive. So we're still running offline RL, and that can also sometimes take a lot of time. And so another question here is, what if we avoid RL entirely? This is kind of the last thing I'd like to cover. And we're going to look at this idea now of active, robust imitation learning, where we're going to take the idea of like mapping directly from states to actions, but we also want to maintain uncertainty. And we're going to use active queries to reduce that uncertainty. And so this is a paper that we have at Coral this year that we call Thrifty Dagger. And so Dagger is basically a way of like making behavioral cloning better by having a human labeler come in and give like all the right actions for everything that the agent does. And as you like repeat this over time, as you have like a policy rollout and a human come in and label what it should have done, eventually it's going to learn the right thing, but it requires a lot of human input. The human has to kind of be constantly babysitting the agent. So thrifty in the name means that we want to like actively query the human for help only when we think we really need it, because we're assuming that the human is the sparse resource that we don't want to constantly be like thrashing and asking them to come help us. Then they go back to their task, and then we ask them to come back again. And so we want to minimize the number of queries that we give to the human. And so the way we do this is we're going to take a state input, S of t, and we're going to train a neural network to predict whether the state is novel. The way we do this is by training an ensemble and looking at ensemble disagreement. If it is a novel state, so something that we haven't seen before, or we're really uncertain about what action we should take, we're going to query the human for what their action would be. We're also then going to look at if this isn't novel. So I've kind of seen what to do here before. We're going to also train a network to predict how risky it is to be in a certain state. So what's the chance of me failing? And if it is risky, I'm going to query for the human again to come in and label an action and tell me what to do. If it's not though, if it's not novel and it's not risky, then I'm going to take my own action. I'm not going to bother the human. And so in this way, we're able to collect data from the human in areas where we think we need help. Either we like haven't seen a human action, or we think that like we might fail at the task. And so for example, this is a task where we're trying to put this washer on this peg in the left. And right now it's autonomous mode. You'll see it misses the grasp. And so then it calls for help because it's in a novel state, and it says, hey, can you help me out? The human supervisor takes over. At some point, the robot says, okay, now I can like take back control. I know what to do. I move along, and I'm going to like insert the washer. Here's another mode where the robot thinks that this is kind of risky, and so it moves it into the supervisor mode. When the supervisor gets the robot arm close to the washer, it goes back to autonomous mode, is able to take over and complete the task. And we've also looked at this in terms of a complex rope manipulation experiment where behavioral cloning here just by itself is not able to perform the task very well. It kind of just gets stuck. Whereas thrifty Dagger, after training and collecting a lot of human actions via this active learning, this is showing like the final train policy, which in this case, we're trying to do this kind of figure-8 pattern. And so it actually successfully learns to do this really long horizon task that's pretty complex. And what's kind of fun is you can look at this. And so this shows kind of like the starting configuration on the left. This is what the goal should look like on the next to most left. And you can also, we visualized some examples of when the algorithm thought it was like novel or risky. And so you can see this novel state, like the robot's like gotten pretty far out of the way of where it should be going to do this figure-8 pattern. And so it's going to query for help and say, hey, human, can you help me? And then human could come in and help the agent recover. There's also like a risky setting here where it's getting a little close to the different screws. And it's also not quite sure what to do. Whereas on the right, it's showing a safe state where it is not novel, not risky. And so in this case, the robot's not going to query for help from the human. And it's just going to continue autonomous mode. Yeah, so in summary, we've talked about a lot of things today. We've talked about how to efficiently represent uncertainty, how we can use that uncertainty to perform robust policy optimization, and how we can actively reduce our uncertainty by querying for more data and getting more human input. And I think there's lots of interesting directions to go in the future. In particular, there's a couple of axes I'm really interested in. One is looking at different types of uncertainty. Another is like different types of human input. And finally, thinking about different ways of defining robustness. So today we've talked about having uncertainty over the rewards or the actions an agent might take. There's also uncertainty over a lot of other things in the world, like your dynamics, object properties, even uncertainty over how optimal or rational I think the human is that I'm getting data from. We've talked about how you can learn from demonstrations, learning from preference rankings. There are also lots of like really rich sources of human data that we haven't talked about today that I think would be really interesting to combine, such as natural language, learning from e-stops, when the human says, stop, you're going to do something bad, corrections and such forth. And we've also talked about robustness in terms of coming up with these performance bounds, being robust to a distribution. I think it's also interesting to think about robustness in terms of verification and certifiability. Can I come up with tests that let me test whether an agent has learned the right thing or not? As well as think about explainability as a form of robustness, where maybe a robot's policy is robust in the sense that it can like explain what it's doing and like make that transparent to the human. So with that, I'd like to end by thanking my brilliant co-authors who've helped on the variety of these projects, as well as wonderful mentors that I've had through the years, Ken Goldberg and Anca Dragan at Berkeley and Scott Niekum at UT Austin. So with that, I'm definitely open for lots of questions. So thank you.
Hey, Daniel, I will kick off with a question. So my question in BREX, you had temporal distance as a like one of the things that you were predicting or part of your loss or something. I'm curious what the intuition or why you think that might be helpful.
Yeah, that's a good question. So the temporal difference or distance, we're basically, given a trajectory, we're going to take like randomly sample 2 states, and then we're going to classify whether they're like a certain range apart. So we had a couple different bins of like, are they like, within 5 time steps, maybe like 10, 50 or 100. And so the intuition there is that that's hopefully going to kind of learn some measure of what trajectories look like and kind of like progress through the environment. And so it's like not quite the same as like just like a forward dynamics model that tells you like exactly what's going to happen in the next step, but gives you some idea of kind of how trajectories progress through the state space, and hopefully it's going to pick up on features. And in particular, I think this was useful for Atari games because there often are these nice visual representations of progress in terms of like, say like in Space Invaders, how many aliens I've hit over time. And so we're hoping that that's going to give us kind of an unsupervised way of learning different features that let the agent kind of know, where it is over time and what's kind of happening through the trajectories.
Thanks.
Yeah, great question. And I guess, to follow up on that, I think that's still like a really open question of like, what is the right type of kind of self-supervised or unsupervised loss functions that do allow you to learn this like nice, rich latent space? And yeah, I think, yeah, recently there's been a lot of really cool work on like contrastive learning. And so if I were to go back and, redo that paper without, what I know now about contrastive learning, I think that would be also something that would be a natural thing to add in there, because that's shown a lot of really good work in reinforcement learning, as well as just standard supervised learning, where I can train unsupervised features and then just train like a linear layer on top and do really well. And so I think, yeah, as unsupervised training methods get better, I think those methods can naturally kind of fit into this type of framework.
Nice.
I had a question about the ordering with the preferences. So if you had a bunch of demonstrations getting you close to a goal, trying to get to a goal state, then you could say how close I am. I could order all of my trajectories by that. But what happens when there's multiple ways to be wrong or multiple ways to be right? I mean, it seems like you might not have a strict ordering over preferences, or you could get a person saying A is better than B, B is better than C, C is better than A.
Yeah.
How much of a problem is that?
Yes, I think that's like a really interesting question. It's something that we haven't done much work on, but I think it definitely could be problematic in some types of settings where, like, yeah, maybe I have two trajectories. The first half of trajectory is really good, the second half is bad. In trajectory B, like the first half is bad, the second half is good. So how can I actually really like come up with a preference over those? And so, yeah, I mean, one way of doing that is to kind of like subsample trajectories. And that's actually what we end up doing in T-Rex, is we actually look at some smaller snippets of these trajectories, which are hopefully easier to compare because it's over a shorter time horizon. And hopefully it's not like going to be doing like lots of good and lots of bad things. And so I think that's like one way of getting around that, but I don't think it like really solves the problem. And so I think, yeah, thinking about like ways of maybe like learning multiple objectives from preferences could be interesting if there's ways of like the human, like, yeah, like specifying that like, hey, there's like a couple of things here, like you were doing like good under A, bad under B. In this case, like good under like C, but maybe bad under A in this other case. And I think like figuring out how to like specify like how many objectives there are, I think is, yeah, a really interesting like research question, and whether you could like maybe kind of infer that would be pretty cool. But yeah, it's something that, yeah, I think it's pretty open. And yeah, I think it's a great question.
Cool, thank you.
Any other questions? If you have for Daniel, please feel free to unmute yourself and ask him directly. If not, then let's thank Daniel for excellent presentation and wonderful conversation during the presentation.
Thank
It
you.
was great. It was great to e-meet you and listen to you today, Daniel. Thank you so much. Thanks, Matt, for bringing him in.
Yeah, thank you for having me.
No problem. So we have one-on-one meeting scheduled for you, and feel free to meet Daniel during those meetings. And if you want to, someone has not yet scheduled the meetings, please email me or Sabina to schedule those one-on-one meetings with Daniel. And we'll see you next week. Thanks, Daniel, for today's presentation. Thank you so much. See you, everyone, next week. Bye-bye.